All right, so I just want to give everybody kind of an idea what we're planning to do with these lessons. So today I'm just going to do like a introduction to kind of what rockets are and give some history. Um, and then the next series of lessons, a couple of lessons will be kind of like theory and physics surrounding it. Then there will be some software mixed in. Probably Aryan's going to be doing that. And there's going to be also technical stuff like how rocket engines work and more stuff surrounding that. So I also want to introduce you guys to and make you aware of what the execs have been doing. So we've been making small model rockets and launching them, and I have a video to share of a recent successful launch.
Three, two, one, go.
So we were pretty happy with that because it actually flew straight. And there's a close-up view. Accelerates pretty quickly, doesn't it?
Three, two, one.
All right, so what is a rocket? So essentially, the idea is a rocket is any vehicle that gains a force from accelerating mass really, really quickly out opposite the rotation, opposite the direction you want to accelerate. So this is what sort of a rocket engine looks like. Basically, what it does is it sends propellant out really, really fast in this direction. And by Newton's third law, it gets pushed equally up, or the opposite direction, I should say. And really, a rocket can be attached to anything. There are rocket cars. The land speed record cars are rocket cars. Um, there's rocket planes. But most of the time, when you say the term rocket, you really mean an orbital vehicle, a vehicle that takes some payload up to space or orbit. So I also want to familiarize you with the fact that rockets come in different classes and sizes. So there are small rockets and very large rockets. So typically, small rockets would be classified as anything with under 2,000 kilograms of payload. And this is an example one. It's called the Electron rocket. And these are getting more and more popular as satellite technology is improving and instrumentation is lighter and cheaper, and more people have the capability to make satellites. Um, and the next class is medium lift launch vehicles. So these are between 2,000 kilograms and 20,000 kilograms. Now, this is the most common class. Almost all satellites are delivered by these types of rockets. They can go to almost any orbit with these, and they balance sort of the cost per kilogram that a very large rocket would offer with the development, because to develop a large rocket takes a lot of development cost and a lot of infrastructure. So it's just a good balance between. And there's also heavy lift rockets. So heavy lift rockets would be anything over 20,000 kilograms. Now, there have only ever been a few of these, and they're very rare because they're very expensive to maintain, and there have only ever been like two super heavy, which is over 50,000 kilogram launch vehicles to fly, which are Saturn V and a rocket called Energia. Now, to show you some more insight on this, I have a picture here comparing sort of orbital class vehicles. So you can see how big the range is, where it goes from maybe like 10 meters tall to more than 100 meters tall. And the smallest rockets can even fit inside the payload bay of the largest rockets. I also have a video to share. So yeah, you can see even small ones are actually pretty big compared to a human, but it gets pretty insane. It gets to the point where it's like a dot, and like the rocket looks like a building almost. Okay, moving on. So let's talk about the early history of rocketry. So essentially, rocketry started at the same time as gunpowder and combustible chemicals. People started tinkering with this technology very early on, but they didn't have the means to accelerate it super quickly. Um, so essentially, the first ones that are documented are Chinese using what are called fire arrows, where it's like a black powder spiked arrow. So basically, at the end of the arrow, they would put a little bit of black powder and ignite it at the same time as they would fire it, and that would give it a little extra kick. And this technology stayed relatively constant up until maybe the 1700s, where iron could be used better. And essentially, the first major improvement since then was what's pictured here, which are called Mysorean rockets, and they were developed by a particular part of India around, yes, late 1700s. And the improvement was that they would have a rudimentary nozzle and an iron casing around it, and they would use solid propellants inside, like black powder and the like. And this is honestly kind of where the execs are in terms of technology at this point. The next major development was made by this guy called Robert Goddard and his team. So his innovation was that he made a liquid-fueled rocket. Now, liquid-fueled rockets have many advantages over solid-fuel rockets. Um, they're able to be turned off and relighted. They're able to be throttled. So those are just some of the advantages. Plus, they have higher efficiencies. They have higher ISP, which is kind of a measure of fuel economy, I guess you could say. More will be explained on that probably in the next few lessons. Now, his flights are actually pretty good. He managed to get up to a few kilometers in altitude, which for his time is actually very impressive. Now, simultaneously, kind of while the people were tinkering with these first liquid rockets, World War II kind of happened and World War One during that time, and people were using rockets as artillery shells. So they would load them up with solid propellants and have maybe a small payload as a bomb. And I would say the Soviets probably did this the best. They had a rocket launcher called the Katyusha, which essentially had several, maybe up to 20 rockets on rails, and they could all be ignited one after another, and they were used for basically bombardment, and they were very effective at it. Now, unguided rockets like the ones before are all good, but they can't really do much because they're not accurate. They can't get into orbit because you need to steer to get into orbit, and you need to respond to sensor data. And this is the major improvement was starting to take data from sensors and guiding the rocket. Now, the first people to do this were actually the Germans with the V2 rocket. Uh, they scaled up all of Goddard's ideas, and yeah, essentially the technology was almost the same. It was just scaled up and had a guidance unit in it. And this was a rocket V2. It was about 1.7 meters in diameter, 14 meters tall. It's actually the first rocket to go to space because they did a test flight where they launched it straight up vertically, and it got up to 203 kilometers. It's also the first supersonic rocket. Um, and then as time went on, after the war, the Soviets and the Americans kind of copied the design and started iterating it and improving it. And also, along with the technological advances of the time, with better materials, better understanding of physics, and also more funding, they began to develop much better systems. And a capability that was introduced was staging as well. Now, this is the R-7. It is considered to be the first intercontinental ballistic missile because it was the first sort of rocket that was able to go more than 5,500 kilometers away from its launch site. This is the definition of ICBM. Yeah, and it was basically it has two stages, right? So it has these side boosters that get jettisoned um, partway through flight, and that reduces weight, and it's basically more efficient to do things that way. Now, I just want to point out to a schematic of the V2 rocket so that we can have a look, and I'll explain some of the features. So it's a bipropellant rocket, which most rockets are, has a liquid oxygen tank and an alcohol tank. Alcohol was used as fuel because it was actually really good at cooling the engine, which is one of the problems they were facing. And you could kind of see here's the bomb where the payload is. Yeah, same thing, bomb and payload at the time. And the control compartments. It's interesting to note how big it is actually, because on modern rockets, the computers are fairly small, and you don't need to have this large control section. But I guess at the time with those computers, they would have to be pretty big. Um, and you can also see the kind of the engine section as well. There's this big gap between the turbo pump, which is essentially the pump that takes the fuel out of the tanks and pushes it into the engine so that it flows really fast. You can see how much space there is with this piping as well. And this is something that is also much better now because the turbo pump is essentially integrated right beside the combustion chamber, and it doesn't take up this much space as well. So that's just some of the interesting things to note about the V2. All right, so after ICBMs were developed, essentially you already had the technology you needed to get to space because they were super powerful, could go a long way, and yeah, essentially it was the same thing. Like a rocket and a missile can essentially fill in each other's tasks, really. Um, so it began to be a race of kind of who could get more firsts, more like first achievements between the Soviet Union and the United States. And in the early phase, since the R7 was such a good design, the Soviets really pushed ahead pretty far, and they got a lot of first achievements. So in October 57, they got the first satellite into orbit. It was called like Sputnik 1, which is literally the Russian word for satellite. Um, And on the very second mission, they got a dog into space as well. So that was the first sort of living organism into space. Now, the first living organism to return was a pair of dogs in August of 1960. And that obviously paved the way. If you can return, a live animal from space, you can probably do a human as well, right? So that paved the way for the first human, Yuri Gagarin, to go to space in April 1961. Next sort of improvement that's worth mentioning is the first multi-human spaceflight, also done by the Russians in a honestly very similar variant of the modern Soyuz capsule they still use, was October 1964. And the first spacewalk, I'm pretty sure you guys are familiar with the term. It's when you leave a capsule and just have a suit on and go out into space. It was done in 1965. Now, all this competition was all this competition led to better and better rockets being developed. And honestly, parallel to this, ICBMs were also being worked on, and the technology is very interchangeable. So between, I would say, 1955 and 1970, there was a super rapid period of innovation where the technology just shot off. Now, the latter phase of the space race was trying to get to the moon, right? And this is where the Americans caught up because they actually radically pushed ahead with their design for the Saturn V rocket after President Kennedy did his "We choose to go to the moon" speech in 1962, and that got everybody really excited for the moon program that they were trying to do. So getting to the moon, it's actually pretty hard. Now, there's this thing called delta V. I'll just explain it briefly. It basically means change in velocity that you have to change to get to a certain place in space, right? Um, and going to the moon takes about 25 to 30% more delta V than getting to low Earth orbit. Now, it might not seem like much, but it kind of scales non-linearly. So to get just a little bit more performance, when you're already high up, you need a really big jump. So that's why these rockets had to be so massive, right? They were over 100 meters tall. They were pretty big. Yeah, the Saturn V, the rocket that successfully flown astronauts to the moon, well, is still the most powerful to have ever flown. And so engine efficiency was improving over this time. And another innovation was the use of common domes, which is essentially using one separator between uh, uh, an oxygen tank and a fuel tank. And that saves weight, obviously. And this is the engine they were using. It's called the F1. It's pretty big. Like it's actually very big. It's the size of a bus. Like you can probably drive a car just into the nozzle, into the no of the nozzle. And they were having troubles with with combustion, particularly with combustion instability, right? Because it's so big, it was pretty hard for them to control the flow of the fuel. And basically, what was happening is they were getting turbulence in the fuel, and this nozzle is designed very much for just laminar flow. And what was happening is it was getting ripped apart and exploding. So they had to fix that with a clever injector. Just the fact to say what was going on during the time. So I just want to pull up a schematic of the Saturn V, if Wikipedia will load. Okay, awesome, yeah. So you can see where the common domes that I was mentioning was. Now the first stage was still separate like bulkheads that they were using for the oxygen tank and the RP-1 tank. RP-1 is just what rocket propellant is also known as. Yeah, this is the common dome, so you can see like the hydrogen and the oxygen were separated by just one. And yeah, I don't know. Some interesting things to know is how it had an abort motor. So if the computer detected a problem with anything on the rocket, it would signal an abort, and the capsule would just fly away to safety as the rocket explodes underneath it. So pretty cool. Now I want to talk about the N1, which was the Soviets' attempt to try to make a moon rocket. Now it was a very different concept in many ways. So the Saturn V, it only had five engines on it, right? But the N1, it had 30 much smaller engines. And one issue they were having is that since their engines were at least somewhat unreliable, they would have maybe a failure per flight, and they didn't have good like safety cells between each engine. So when we would have an issue and an engine would explode, it would break the other engines near it, and this issue would cascade very quickly and destroy the rocket. And I know another interesting fact is how there's fence-like interstage separators, and this is done because the Soviets, their philosophy was to just hot fire the next stage while the first stage is close to shutting down. So, and then they would separate. And this is done because your fuel is under load and it's at the bottom where the intake is. Otherwise, you separate, you have a moment of zero gravity, right? And the fuel just kind of forms a ball and sloshes in the middle of the tank. And the Americans would have separate motors, smaller rocket motors that would be used just to get the fuel to the bottom of the tank. But the Soviets wanted to avoid that complexity. Okay, so the Apollo program was very expensive. Um, it cost them $200 billion, and that's just for 10 launches. Now that factors in development as well, obviously. So it was an unsustainable way to explore space, so it ended up getting canceled in 1972, and then instead, the States developed this thing called the Space Shuttle. Now, the original idea with the Space Shuttle was to make a fully reusable vehicle, but quickly, and that could land on Earth as well in one piece. Now, quickly they noticed that that was not feasible, so they had to cut back and expend a portion of it, which was this orange fuel tank here. Um, now, so this program ran from 1981 to 2011. It was the first large-scale rocket to use hydrogen fuel. Uh, it's the only system ever to be designed that could carry astronauts and a significant payload at the same time. Now it still has the largest payload bay or payload compartment out of any vehicle ever developed. In case you don't know this, this wasn't one vehicle. This was five separate. The orbiter, which is the part that actually went to space that looks kind of like a plane. There were five of these made. The orbiters, yeah, they would re-enter and land on a runway. This is a unique capability that has never been done since. Uh, they reused for this program a lot of the old Apollo infrastructure, though. They reused the vehicle assembly buildings. They reused the launch pads and all the space centers that they had made for Apollo very much came in handy. Now, this was a flawed system, to be honest. Like, there were two major catastrophes, uh, and there wasn't even an abort system that was available for them to use, unlike the Saturn V, which I showed recently, right? Just a few minutes ago. Uh, some of the issues again are like the SRBs, they're dangerous because they can't get shut down. So if something is wrong with the SRB, there's no way to escape since there's no abort system and there's no way to shut down the engine as well because it's a solid fuel and there's no way to cut off the combustion. Also, the heat shield was very delicate that they had to put on there because it was designed to be reused many times. So over time it got worn down and was could be damaged easily. Now let's talk about the two major catastrophes they had. So they had the first one was in 1986, which was Challenger. I think a lot of you are familiar with it. This was caused by a leaky SRB. So one of the joints between the SRB segments uh, was not functioning properly. So basically, it started expelling hot gases up just over the strut which held it in place to the tank. So essentially, what happened? Those hot gases cut through that strut, and then the booster pushed into and ruptured the fuel tank, and yeah, it broke apart from aerodynamic loads as well, and some of the fuel exploded as well. Uh, yeah, and then the next catastrophe was Columbia. So basically, what happened with Columbia on its way to launch, there was a piece of debris from the top of the tank that hit the leading edge of the wing, and what that did, it was broke one of the plates that are necessary for heat shielding when you're re-entering orbit. So what ended up happening was when they try to re-enter, the plasma from re-entry, because they were going super fast and hitting the atmosphere, the plasma ripped through and cut through the wing. But it was even with these issues, it was still a successful program, very successful actually. Uh, some of the accomplishments were that it built the ISS. All the large modules were taken up on the space shuttle because it was the only vehicle capable of doing that. It sent Hubble into space, and it actually did several servicing missions that extended the Hubble Space Telescope's lifetime. And the Hubble is a super important scientific instrument. 355 unique individuals went to space on it, with 852 human space flights. That's like a trip to space, counting repeats, of course. And there were even a couple of astronauts that flew on it 7 times over. So commercialization of space. This is a very, well, not very, but it's a trend that has been going on recently, somewhat recently, maybe since mid 2000s, where private companies are developing their own launch systems, owning them and operating them by themselves. So the first privately owned and operated rockets, again around early to mid 2000s, were made by large defense contractors like Northrop Grumman and ULA. ULA is United Launch Alliance. It's a joint venture between Boeing and Lockheed Martin. I'm sure most of you have heard of those companies, right? And those big defense contractors, they had the resources since they were already working on NASA vehicles as a contractor. They already had a bunch of resources put in place so they could easily make their own system, which they own. And they did. Now, an example is this one here, Delta IV. It's currently the largest actually operational rocket in terms of, I guess, vehicle proportions or size, but it's actually not the most capable. It's not the most powerful. It's a fully expended system. Like an interesting fact is, even though it pushes out hydrogen, which should be clear, you can still see this orange flame because an interesting fact, it's like the nozzle is ablative, which means it erodes as it gets heated, and that adds to this sort of color, which is kind of cool, I think. And with these expendable systems, the build quality can be cheaper as it goes through less cycles, but this is still one of the most expensive rockets to operate. Like it costs 300 million to launch, um, but it's tailor-made for national security space launches for the U.S. government. Now, the first company to break through without being previously a large defense contractor, first company to break through and actually launch a vehicle to orbit was SpaceX. Now, what they did in 2008 was they got a Falcon 1, which is a smaller sort of variant of this Falcon 9, which I'm sure a lot of you are familiar with. They got it into space after 3 failures and they were on the brink of bankruptcy, but they managed to do it. And they're very successful at the moment. Now, this Falcon 9 they've developed has a lot of interesting and new capabilities. So it is the first rocket to be able to land the first stage. So up to about here, this when it separates at staging, this part actually comes down and either lands back on land or on a boat. And this is good because you can reuse it afterwards and not have to spend that money to make it. So they also reuse fairings as well. So at staging, what happens is, sorry, not staging, right after staging, after the aerodynamic stress is not as much, they can shed these fairings because they no longer need to protect the payload from the air pressure. And they catch those on boats with like large nets as well. And that's also significant. Like each fairing could cost upwards of $1 million. So it's not completely insignificant. And the most, so I just want to mention the most reflights they've had, or I should just say flights, they've had with a booster is 7, uh, which is pretty good. And they're trying to get to at least 10. It was designed to do 10, and hopefully they can do even more than that. And it's the cheapest sort of, I would say, properly sized rocket. It costs 50 million per launch, which is actually insanely well priced compared to other rockets of similar capabilities. All right, I want to show you a video of what a first stage landing looks like, because that's a really interesting capability. I'm sure many of you have seen this, but for those who haven't, it's pretty cool. So the rocket, yeah, after it separates, this is just the booster coming down. It has to light its engines to protect itself from re-entry pressure, or heating, I should say. And boom, lands right on the ship. Pretty cool. Nobody has ever done this before, and nobody has done it since. Okay, so another interesting company that has recently gotten success is Rocket Lab. So they were, I guess, they are the second company to come out of nowhere and make a rocket. Like I said, they weren't like some kind of defense contractor beforehand. Now their focus is on much smaller rockets. So basically, um, beforehand, right? So let's say like 30 years ago, the only people that developed rockets were the U.S. were governments, right? Um, and what they did is they made large rockets that could take national security satellites, which are pretty big, and then that technology kind of trickled down, and people had to make big satellites because they were big rockets, and that was it, right? But Rocket Labs wants to create a new trend, which has already been going on, but they want to accelerate it, which is making smaller, maybe 300 kilo satellites. Now, if you think about it, 300 kilos is actually quite a bit. Like you could put a lot of instruments in a 300 kilogram object that can do some kind of science or research or some kind of technological purpose in space. And that is their goal, to make it as cheap as possible for those types of people. And what they're doing is 5 million per launch. So it's like way out there in terms of the cheapest one. But the cost per kilogram isn't so good. Now here's some future rockets that are going to fly hopefully very, very soon. So I'll start off with SLS. So it's kind of it's NASA's next moon rocket. It's a part of their Artemis program, which is the program to get flights, get people back to the moon for the first time in 50 years, and the goal is to get it flying by next year. Now, you can see the similarities with the shuttle, I hope, right away. You see how the solid rocket boosters are essentially the same. It uses the same engines, the exact same ones. Like literally, they're going to take engines that have previously flown on shuttles, remove them, and put them on SLS rockets. And these engines are already like 40 years old from the 1980s, but they were made very well, so they can still be used. And yeah, it's obviously the hydrogen tank. It's the same diameter, very similar, and yeah, that's it. It's a pretty capable rocket, but the drawback is that it's super expensive. The projections are currently for it to cost $2 billion per launch, which is insane when I just mentioned that SpaceX does Falcon 9 for 50 million, and this is billion with a B. So remember the Delta IV I showed on the last slide? This is called the Vulcan rocket. It's made to be as like basically a direct replacement. And ULA, what they're doing, they don't have any radical new sort of systems. They just want to like make everything a little bit cheaper for themselves, maybe add a little bit more capability, a little bit more safety. Um, they changed the fuel as well. They're using methane now instead of hydrogen because hydrogen actually has a lot of drawbacks. Even though it's can be the most efficient, it's hard to work with and requires insulation. And there's a lot of other drawbacks. But yeah. Now, actually, one thing they're going to try to do eventually is jettison the sort of engine compartment and recover the engines sort of downrange on the boat, which is pretty cool. Like the engines are very expensive on rockets, probably the most expensive component. So at least they're trying to save some money and go for reusability. Now, this rocket here, it's called New Glenn. It's going to be made by Blue Origin. Now, uh, I think you guys are probably familiar with Jeff Bezos, the richest man in the world. Guess what? His side project is funding a rocket company. Um, so what they're going to try to do is basically copy the abilities of Falcon 9, but do it bigger. So this one can land the first stage, uh, reuse it. They might even reuse fairings as well, and it's going to be very big. This one's like almost as big as the Saturn V, which is kind of insane, honestly. It's 98 meters tall. Now, it is important to know that we don't know too much about it because Blue Origin doesn't post a lot of information to the public, let's just say, and they don't need to because they have no risk of dying because or going bankrupt because they get a billion billions of dollars each year injection from of cash from Jeff Bezos. Now, the final vehicle on the slide on the right, it's called Starship. This is honestly the most exciting out of all of these by far. It's what SpaceX are developing as the next rocket that they want to do. It's fully and rapidly reusable. So they want to land the booster right down where it launched from, take another Starship. Starship, like it's called the upper stage. It's kind of weird. The whole vehicle is called Starship, but the upper stage itself is also called Starship. I say upper stage to be more clear. So yeah, launch a booster, land it right back on the launch pad, take an upper stage with the crane, lift it off, and then fly it right away. Like they could launch with the same booster once every couple of hours. That's the goal long term, right? Yeah, and then the second stage can also come down, obviously, and land as well. And yeah, it will be the largest rocket ever. Like you can see, 118 meters. It's pretty big, 9-meter diameter. And the most insane thing ever is that since it's every single component is going to be reused, they're wasting nothing. So it's only going to cost like fuel and support, like labor on the ground of the people that need to do launch operations, right? So the estimate is like $2 million per launch, which is absolutely insane. The fact that it's cheaper than that tiny Electron, yeah, this thing's going to be insane once it goes. And the plan is honestly for, I mean, Elon says it's going to go next year. I hope it does, but kind of doubt. Yeah, what else? So it has a novel re-entry technique. So the Falcon 9, when it re-enters like with its engine compartment pointed towards the direction of travel. This one is gonna point its like belly towards the direction of travel to try to take full advantage of atmospheric heating, or sorry, not heating, drag. But I mean it's heating too, comes a result of that. So it needs a heat shield on there, which it will have. Yeah, and it's doing this because it's not coming. Look, so the Falcon 9 first stage, it comes in at like 5,000 kilometers, maybe like up to eight, right? And then this is going to come in from essentially orbital velocity. So that's 25,000 kilometers an hour plus, which it's a huge difference. So it's going to be pretty difficult for them to solve this problem, but I hope they do. Now, another thing they're going to do with it is refuel it in orbit. So the second stage is going to take some fuel to get up into orbit, right? And once it's in orbit, they're going to get another one, which is just a tanker. So it's not going to have any payload other than fuel. It's going to go up, give some of its fuel to the rocket that's which you want to do something else with, like your main rocket that you just launched, land, and they can do several cycles of that and completely have a full tank on the second stage. And this is done because they need that to be able to go to Mars, which is obviously, if you know Elon, that's what he wants to do, right? With his company, SpaceX. Oh, and one more thing to mention. SpaceX want to do Earth to Earth missions, or I guess, yeah, I guess you could call them missions, um, where they would just take a second stage and put it on a suborbital trajectory as a transportation system. So, for example, you could get in, where are we? Toronto, right? Let's say Toronto. You could get into a Starship and be in Hong Kong within 40 minutes, because that's how fast rockets can go. All right. So I want to talk about like some far future, maybe not so far for some of them, but some of them are really far future concepts. So the first one is this is just a propulsion concept. It's not a vehicle concept. So solar sails. So what these are is instead of kind of taking capturing the pressure from the wind, which sails do here on Earth, they capture the pressure from solar radiation. Now, they take a very, very long time to build up speed because it's a very slow process, but they can get to really high speeds. Some ideas are is to point a laser at them so they capture the like the light energy in the laser, like from Earth, like a high-powered laser right to where the ship is. But this is going to be a difficult problem to solve, and it's actually kind of interesting. You can accelerate into almost any direction with clever manipulation of the sails, kind of like how sail ships can travel like straight into the wind. And a good thing about this is since you're not expelling propellant, your ISP or range is infinite. You can go wherever. But yeah, it's a drawback is how slow it's going to accelerate and how big it has to be. Because yeah, it won't accelerate at all pretty much unless it's big. And they have to solve the problem of heating as well, right? Because you want the the radiation pressure not to turn into heat. You want it to turn into uh, speed. And yeah, that's important. Now let's talk about some nuclear propulsion concepts which have still yet to be used. Some of them have been demonstrated on a smaller scale, but yeah, they need to still get developed. So the first one is called nuclear pulse propulsion. Now, what this does is it captures the energy from essentially nuclear explosions and pushes them out a nozzle, and yeah, you can accelerate from that. Now, if you can capture it well, then it's actually very powerful, very efficient, but it's pretty dangerous and hard to develop, right? Because nuclear testing is now by treaties restricted to only underground. So this probably won't happen anytime soon. Next one is nuclear electric. So the idea is you have a nuclear reactor, generates electricity, just like any other nuclear reactor or power plant there are today. Um, but uses electricity to power an electric mode of propulsion, like ion propulsion. And these modes of propulsion are being used on very small thrusters for satellites to maintain their orbits. Um, but they haven't been increased in size. This is a big problem. They don't work as well. They become much less efficient if they're increased in size. And engineers will have to figure this out. There's also nuclear thermal propulsion. So this is kind of like, what if, a fission reactor, how it reacts, say, with water and generates steam. Um, what you can do is pump a working fluid through it, or like anything, water, hydrogen. Hydrogen is probably, from what I've read, is the best. And what it does, the working fluid gets heated to high temperature, and then with that thermal energy, it gets pushed through a nozzle, much very similar to how chemical rockets do it, and it can be very efficient, like with ISPs of up to 800. Again, in a future lesson, we will explain exactly what ISP is. Okay, so, and these are some far future ideas that I just want to kind of mention. So there's antimatter propulsion. So this is using antimatter as your propellant. Now, antimatter is insanely expensive to manufacture. We don't really have the capability to manufacture it at all, even if we had the money, right? Like just beyond what we have now. But it would be good if we could, because the energy density is higher than normal matter. Um, and then there's photonic rockets. Now, this is a concept where you would direct photons, so this is light basically, out of your engine into just one direction. And this would be insane because it's coming out at the maximum exhaust velocity like possible. So you get the highest specific impulse possible. Okay, so let's kind of change the tone. I want to talk about a rocket countdown process, the rocket countdown process. So just going to be general, kind of what things have to be done for a rocket to launch. And this is going to be pretty similar for all rockets. There will be some variations, of course. Actually, a lot of variations, but there are some general strokes that are the same. Okay, obviously you need to clear people off of your launch site, right? From rockets, the exhaust is very, very hot, so you'd probably get fried within, I don't know, 50 meters radius, and you'd be deaf within maybe 200 to 300-meter radius, something like that. So, and just for safety, typical exclusion zones are like 3 kilometers or more. So, yeah, you need to clear people of the launch pad is definitely. Then fuel up can begin. So this is where you take an empty rocket and then take some tanks on the outside and start putting the fuel into the rocket. This is varies quite a bit. So hydrogen, it's for hydrogen fueled rockets, it's typically a lot of time, like 5 hours or more. But for RP1, kerosene, RP1 kerosene can be used interchangeably, I guess. It takes much less, like maybe 40 minutes. The computer has to get transitioned to flight configuration. Again, this can vary a lot depending on the rocket, depending on the computer, but basically this is just one of the steps you need to do to arm the computer and get it ready to start up and fire the rocket. Okay, so engine chill. Engine chill basically means, so almost all nozzles are regeneratively cooled. So this means that the propellant is pumped through the walls of the nozzle to keep it cool, right? Because it's getting this insanely hot gas, and the combustion chamber, of course, as well, because you get this insanely hot gas going through it, and you need to keep the metal from, or whatever material they're using, from melting. And that's just to introduce to the fact they need to get propellant in there. Now, on a lot of rockets, propellant is chilled down so that it's more dense, so you could pack more of it in. Now, if you shock the metal, it's just not good. It puts stresses in. Right. So imagine like there's no engine chill, and you just suddenly pump insanely cold propellant into some pipes in metal. It's not going to be good for the metal. So what they do is gradually cool it down so that it's ready for that. Anyways, that was a bit longer than it had to be. The explanation. So internal power transfer. So what this means essentially, so the rocket has some electrical systems on board. Uh, I mean, every rocket does, right? And what they do is they no longer draw power from the umbilicals. So umbilicals are basically things that are attached to the rocket to supply it with whatever it needs, like power, fuel, anything. So yeah, it has to transfer to its own internal batteries and power. Arm range safety. Okay, this is interesting. So basically, every single rocket has to have something called a range safety device or flight termination system. What this is designed to do is basically blow up the rocket if anything, like on purpose, if anything goes wrong. So imagine this scenario, right? Like an engine gets stuck and it's gimbaling the rocket back towards land. And it's stuck in that position and it could crash into land. What the range safety officer will do is blow the rocket up so that it can no longer go anywhere and it just falls into the ocean, right? So those have to be armed as well so that I guess they don't go off accidentally. Tank pressurization. Okay, so it's good. There's many reasons why they do this, but it's just basically more efficient to run a rocket when its fuel tanks are at a high pressure. So what they have to do is the fuel up pressure is lower, so they usually these propellants are like liquefied to a cold temperature, so they will like start warming up and expand, and that will pressurize the tank. So all they have to do is close some valves, and that's what happens. So, and then within a minute, computer starts issuing startup commands. So yeah, many things in an engine, like fluids have to be in the right place, things have to be armed, things have to be in correct positions uh, within an engine in the rocket itself. So a computer will start issuing these commands within a minute of launch, let's say. Again, varies. Sound suppression system. So uh, rockets are insanely loud, and sound is very powerful when it's at super high levels, like it could be with rockets. So they have to try to stop that somehow. And the best way to do that is um, basically spray a bunch of water where the engine exhaust will be. And what it does, it converts the sound to steam. Um, so yeah, and that basically makes the rocket launch less violent to the structures around it, right? And then usually within 5 seconds of liftoff, the engines will ignite. And then what the computer has to do is make sure everything is working properly. So there's probably like a gazillion sensors on a rocket engine. There's pressure sensors, temperature sensors, flow rate sensors, a million things, right? So the computer quickly checks, okay, this sensor good, this sensor good. Boom, 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 goes through every single one. And if it's good, a bunch of things happen at once. So hold down clamps are released, or explosive bolts are blown up and let the rocket go. Um, and for some rockets where the umbilicals are still attached, right up to T0, they have to get disconnected. Okay, so rocket launch timeline. So this is after takeoff. What happens after takeoff, right? Um, so first kind of thing is to clear the tower, which is there's almost always a launch tower right beside a rocket um, that is used for like, maintenance and stuff like that. That's kind of usually the first milestone. Then there's what's known as a pitch over slash roll program. So to get to space, you have to go straight up, right? But to get into orbit and stay in space without falling back down, you have to go sideways really fast. So there's kind of a natural uh, shape of your trajectory that you have to take that's most efficient, right? So you don't go straight up, then turn and then accelerate sideways because that wastes some efficiency. There's just like gradual like roll that you have to do, or sorry, pitch over. Roll is different. Roll is when you rotate around your long axis to point your rocket in the most way, in the most stable configuration, and point it into the correct direction as well. So when you're launching from a launch site, there's a bunch of angles that you can launch at, and you have to be on the correct one. So that's what guidance essentially does in the first 10 seconds of flight, or yeah, something, sorry, 10 seconds and more. Usually it starts at around 10 seconds and it lasts essentially the whole way, right? Uh, Supersonic speeds typically happen, I don't know, within after 30 seconds, up to maybe about 45 seconds, and this is followed very closely with max Q. Now, max Q means basically maximum aerodynamic pressure. It's when the loads of the air on the vehicle are the highest, right? Because basically aerodynamic stresses are a combination of how fast you are going uh, and the air pressure. And when you think about it, what happens, right? So you go faster and faster, but the rocket is getting thinner and sorry, the air is getting thinner and, and thinner. So there's a crossover point where those two factors are maximized, and then it just falls off down to zero. When you're in space, aerodynamic pressure is zero. And then three things happen always, pretty much for every single rocket, very close to each other, and that's main engine cutoff, staging, and secondary engine start. Uh, Now, I think it's pretty self-explanatory what these are, right? It's okay, so referred to as MECO and SES in the industry. So your first stage will turn its engines off, then either clamps or bolts, depending on how it is, will be blown up or released. Then you will have the reaction control system, which is like kind of like small thrusters um, that are not powerful at all, but are powerful enough to just slowly give some space between the two stages. Those will fire for a bit, and then hopefully not too long after main engine cutoff, you'll have your second stage start its engine. And yeah, usually soon after that follows kind of fairing separation, which essentially means that the protective cover that's over a payload will separate, right? Because it's dead weight essentially once it's no longer needed. Yeah, and then your engine will just reach a point where it's where there's nothing much else to do really other than just keep going with your engine lit until you reach typically 26,000 kilometers or more for orbital velocity. Yeah, and then it gets cut off when it does so at around 8 minutes or more. I think the fastest the rocket ever gets to space is 7:30. Or sorry, not space, orbital velocity. That's what I meant to say. And yeah, typically soon after payload separation happens, and that can vary like a lot. Sometimes it gets separated days afterwards, depends. And just to mention really quick, what spent stages do. So first stages fall down, burn up, crash, whatever, sink to the bottom of the ocean if pieces still remain. Engines without any second stages, the ones that go to space, just stay in space, right, without any intervention. So what happens is they either do deorbit burns, where their engines retrograde, slow their velocity down enough to fall into the Earth, or what they do is adjustment burns if they're in a high energy orbit. So say like geosynchronous. There's going to be an orbital mechanics lesson, by the way, and I'll explain all about what that means. So that's just a higher energy orbit, and there's not going to be enough, obviously, propellant or delta V to get back down and fall into Earth. So what they would do is there's pre-designated graveyard orbits, which are orbits that are known to be full of spent stages, and it will push those out. It will push itself out to that orbit, essentially. Yeah. Now, I'm sure a lot of you have seen a rocket launch, but for those who haven't, it's pretty cool, and I think it'd be cool to show one really quick. It only takes 10 minutes, as you can see. So that's the rest of the lesson. And then I'll have a question session at the end. All right, I'll leave you to watch that for those who want to. And I guess you can ask questions, and I'll answer if I know the answer. Yeah. Feel free to unmute and ask a question if you have one. Hello. Sorry, can you repeat the question? So you're asking like how many of these concepts have we applied in the actual rocket? Well, this was just a history lesson, right? But yeah, for sure. So, like I said, we just have a outer shell. It's just one. It's not even a tank because it's solid fuel, so it's not like it's doesn't flow out anywhere. So it's kind of like a sticky paste uh, that just stays in a tank. And we do have a nozzle, I guess. So I briefly mentioned nozzles. We'll go into more detail about that later. We have a nozzle that we use for the engine, and yeah, I guess that's out of the things I mentioned today, that's probably the only thing. All right, any other questions? Yep, yep. Let me just read general really quick, see. Okay, Aryan, you said you were taking attendance, right? Attendance is complete. Awesome. Okay. Sick. Okay, wait. I'm back. Okay. Yeah. All right. Yeah. Sorry if I missed anything. Were there any like questions asked or something that while I was having internet issues? There was nothing. Okay. Good, good. Yeah. I've I've applied. Okay. OMB asked the question, what is the point of sending a Tesla up into space? What's the use? Okay, so basically this mission here, it was just a test flight because it was the very first time this particular rocket was flying. So typically customers don't want to go on for the don't want to go for the first launch of a rocket because it's still not proven, right? So since Elon owns Tesla, or sorry, Elon owns SpaceX, right? And he owns his own Tesla. He just put his Tesla as a mass simulator, basically, on it. Yeah. So Elon is a Chad. That's true. Yes, he's doing self-driving cars. It's pretty good. No, no, I think QW takes into account both grades and DC. I don't think there's a cutoff where like yeah, yeah. No, but I mean like there's not a there's not like a cutoff where they don't care about your mark anymore and they start looking at only ECs.